Unlock the potential of artificial intelligence. Welcome to deep learning and generative AI.
Moving a large language model into high-traffic production exposes rigid hardware limitations. The computational load multiplies as models transition to massive, simultaneous request pools. This 3D architecture stack represents the LLOps playbook. It is a layered, rigid production framework required to manage the high-frequency demands of these models without a system collapse. This memory anatomy diagram identifies the primary hardware constraint. The true bottleneck is VRAM. While nodal weights remain static, the dynamic KV cache grows linearly with sequence length, eventually exhausting VRAM capacity. This memory saturation threatens critical service-level objectives, specifically median latency and time to first token. Without an architectural solution to these memory constraints, scaling generative AI becomes financially and computationally unsustainable. Before building the software stack to address those constraints, we must define the hosting environment, as it dictates the required optimization strategy. This spectrum slider illustrates the fundamental deployment trade-off. Cloud deployments prioritize operational ease. On-premise setups offer strict control but high complexity. Edge deployment places models directly onto local hardware. Operating offline requires aggressive model quantization, reducing the precision of internal weights. The chosen environment sets the memory ceiling, forcing architects to align serving methods with physical hardware limits. This contrasts monolithic architecture with disaggregated microservices. Traditional monolithic systems, bundled together, bottleneck instantly under generative AI traffic. Scaling requires decoupling retrieval processes from GPU-heavy inference. This allows the system to process data searches independently of matrix multiplications. We manage this decoupled system using an API-first paradigm. An API gateway, built using Fast API, receives client requests and routes them to backend services. Its rate-limiting function is the primary defense for managing strict GPU quotas, preventing hardware overwhelm. Below the gateway, we must decide between stateful and stateless management. Stateless REST, a protocol where each request contains all necessary processing information, enables the rapid horizontal scaling required for high-traffic applications. Controlling this disaggregated architecture through a rigid API gateway transforms a fragile implementation into a resilient enterprise-grade network. Maintaining this network requires an automated CI/CD pipeline for testing and releasing code safely. Step 2 involves packaging the LLM, GPU drivers, and Python environment into Docker containers, ensuring identical model performance across different server environments. To manage containers at scale, we use Kubernetes, an open-source system for automating distributed complexity. Incoming traffic is split by a load balancer across replicated pods. If a pod fails, the replica set automatically spins up a replacement. This architecture enables independent scaling. If translation requests spike, that microservice scales up individually without affecting the performance of retrieval or generation services. Kubernetes provides the autonomic control required to keep a decoupled application balanced under real-world traffic volatility. At the base of the software stack sits the inference engine, executing model weights directly on GPUs. This table evaluates the primary inference serving stacks. vLLM is optimized for high-throughput text generation and concurrency, while TensorRT-LLM focuses on extracting maximum raw performance. These engines utilize continuous batching, dynamically injecting new requests as computation slots open to eliminate wasted GPU idle time. To mitigate the fragmented KV cache, page detention treats the cache like virtual memory, breaking it into non-contiguous blocks to increase concurrency. Model compression reduces memory requirements. Quantization scaling cuts data precision from 16-bit to int8 or int4, shrinking the footprint. Speculative decoding further reduces latency. An efficient draft model generates candidate tokens, which a larger verifier model quickly approves. These specific engine-level optimizations, page detention, and continuous batching, are the mechanisms used to overcome the physical VRAM limits inherent in large models. High-performance engines require high-speed data delivery. This multi-tier caching strategy replaces slow retrieval. JobLib stores numerical embeddings to bypass the encoder, while intermediate tensors are stored in Redis for near-instant retrieval of frequent queries. We optimize retrieval-augmented generation, replacing sequential blocking with parallel asynchronous queries. To maximize accuracy, hybrid retrieval merges semantic vector embeddings from FICE with exact keyword relevance from the BM25 ranking algorithm. This three-step cycle illustrates the automation of knowledge graphs. Knowledge graphs store information as connected nodes. NLP models extract entities from raw text, and automated scripts merge them into existing graphs to provide continuous context. Advanced retrieval architectures ensure that inference engines receive highly relevant, pre-processed context with minimal input latency. Maintaining an optimized stack requires continuous observability to prevent silent failures. This dashboard displays active monitoring of latency and error rates. We track time to first token and hardware usage against SLOs, using Prometheus, which collects live metrics, and Grafana, which visualizes them. This observability allows for automated governance. If median latency exceeds established thresholds, the orchestration layer can automatically trigger a rollback to a stable system build. Granular monitoring transforms a volatile model into a predictable and manageable enterprise asset. This is the assembled LLM Ops tech stack. The foundation combines infrastructure and quantized hardware with serving engines like vLLM and TensorRT. Above sits orchestration via Kubernetes, advanced workflows using face and knowledge graphs, and an API gateway for routing and observability. Scaling AI relies on this intersection of machine learning expertise and rigorous distributed systems engineering. These engineering layers transform raw computational power into a reliable, concurrent enterprise service.